currently studying the problem of a thin film moving down an incline with a contact angle. Let us first quickly recap what we have seen in the previous lecture, what we have done in the previous lecture. So we chose a thin film flowing down an incline where the contact angle is theta. We've chosen the characteristic velocity to be the average velocity in the thin film. We also said that the capillary number uh, is very small, and this allows us to uh, employ the lubrication approximation, where the small parameter was capillary number per 1 by 3. And using this kind of a small parameter, we wrote down the non-dimensional equations. That's equations 3, 4, and 5. That's the governing equations. And we have another 5 boundary conditions: kinematic condition, the stress-free condition at the free surface, then the normal stress balance, which just says that the pressure is nothing but the pressure in the thin film is basically the curvature, related to the curvature directly. And we have the usual no slip and no penetration condition on the solid surface. Now, what we did was we employed the same procedure that we had done in earlier lectures, especially, let's say, a lecture on free surface flows for thin films, where we looked at the stability of a thin film. Our first goal was to derive an evolution equation for the height, and that's exactly what we've got. The evolution equation for the height turns out to be a partial differential equation. It has 4 spatial derivatives in x, which means that we will need 4 boundary conditions in x, and it has 1 time derivative. That's the initial condition. So now we have an initial value problem, a mixed problem actually. And let us proceed by describing the boundary conditions for this problem. So the part 2 of the lecture begins now. The governing equation you can see on your screen. The first condition that we have is we have employed the lubrication approximation. So what does it mean? For lubrication approximation to be valid, the contact angle needs to be small. Angle that we have chosen, we've called the contact angle as theta, must be small. Now question is, what is meant by small? How small is small? So the idea is follows. So in reality, if we say that the contact angle is small, then locally, if this is the plate, the bottom, then the free surface essentially looks practically like this. It's a very small fine wedge, and the angle for me is theta. That's what we essentially mean by small. Now we can quantify this more precisely in terms of our small parameter, that is capillary power 1 by 3, in a minute. So let's say this is dimensionally, this is how the thin film looks like. If I take a small change in x, variation in x, then the change in y would be, the change in the height would be given by dh. So in other words, this figure that we have drawn here is clearly not to scale. So we are really looking at a small region here near the contact line. Okay, that's this is how it's actually supposed to look like. It's supposed to be a very thin wedge. The idea is that we want to rescale this plot and basically get a wedge with a comparable height. And if we get a wedge with a comparable height, then we have dh and minus dx. They're non-dimensional variables. Remember, the h and x are non-dimensional variables, and the original tilde with the tilde are the dimensional variables. So we know that tan of theta is approximately theta, and therefore it implies that theta goes like dh by dx. That's what we have for theta. And we already have done the case where we said, since h tilde, it goes like order d, the thickness, whereas x tilde goes like order d by capillary power 1 by 3. That's a non-dimensionalization that we employed. It straight away means that theta goes like capillary 1 by 3. And therefore, if CA is much smaller than 1, then theta is also much smaller than 1. That's what it means. So it's a small angle. Okay. Therefore, what we will do is, if we want to get a wedge which is not so small, where everything is order 1, then we'll define a new rescaled angle. Let's call this as beta, and this rescaled angle we'll call it as theta capillary power minus 1 by 3, where beta is the rescaled angle. Then the boundary condition at the contact line, which we'll call it as xc. The boundary condition at contact line essentially becomes hx at xc comma t is minus beta. Okay, so we'll give this a label. We'll call this as equation number 15. Okay, so in other words, we're just saying that we've basically got dh by dx to be theta. To be more precise, we should be writing minus dh by dx to be theta. Let's put a minus sign here. Minus dh by dx to be theta, and therefore if I rescale theta, I simply get h of x at the contact line to be minus beta. So what is this xc? Xc is basically the contact line position. So I have an interface. We have a plate here like this, and we have a thin film which is coming down, and we have a thin film that's coming down and meeting the plate at a particular position, and this particular position we call it as xc. Okay, now we can also do one more thing, not just calling it as xc. We can actually say the coordinate system, the origin is in such a position that we can say x is equal to 0 here. So for me, x is equal to 0 is fully developed thin film. Meaning it is actually sufficiently far away. xc is the location of the contact line. xc is still, by the way, unknown. Where xc is still unknown. But essentially it says that x is equal to 0 is far away, far upstream, and xc is the far downstream location where we have the contact line. Okay, so we've got the first boundary condition. Now we will also assume that beta is constant and independent of time. Okay, that's what independent of time. We also will say it is independent of contact line speed. We will see later that this is not true. The contact angle does depend on the speed. We saw some hints were available when we looked at the problem of contact angle hysteresis. But we will return to this when we look at the relationship between the angle and the velocity in the next lecture. So the idea is that here now we can also say that this velocity contact line position is xc, and this is a function of time. Okay, and it has to be determined as part of the solution, right? But we also know one more condition. At the contact line, we know that the thickness of the interface goes to 0. The next boundary condition is at the contact line, h of xt is 0, right? And therefore, this is another boundary condition. We'll call this as equation number 16. Okay, this is the definition of the contact line position, because that's where the interface makes contact with the solid. Okay. Now we also need boundary conditions in the far field. Assuming the film is flat near x equal to 0, we have h is equal to 1 and hx is equal to 0. The slope of the interface is also 0 because it's basically flat. This is at x equal to 0. So this is the next condition. We have 17. So now we have basically got 4 conditions in x, 15, 16 and 2 conditions 17. But of course we have introduced one unknown into the problem in the process, which is the location of the contact line itself, right? Now we also need some initial condition. So let me just write down what I just said. Equations 15, 16 and 17 give us 4 conditions in x direction. These are 4 boundary conditions. We need one initial condition. Okay. Now how do we do the initial condition? The idea is as follows. Let's convert this problem from a time dependent problem to a time independent problem. So why is it a time dependent? Why is it a time dependent problem? The idea is as follows. Let's consider a flat surface over which there is a thin film. Correct? The location of the contact line is shown by this. This is the location of the contact line. Now what I want to now do is I want to say what would happen to this flat film after some amount of time. Now after some amount of time, this interface is actually moving down, and it's going to test my drawing skills, but that's what is, hopefully it's a yeah, you have to assume that the shape hasn't really changed, or maybe let me have a go at it again. Okay, well, so we say that the shape hasn't really changed much. We assume shape remains the same, except that the contact line has moved downwards. That's what has happened. So the contact line as a whole, the entire thin film as a whole, has slid downwards, but the interface itself, the interface shape overall has remained the same. So this gives us immediately an idea. If I somehow know the speed of the contact line, if I say that the speed of the contact line here, the rate at which this whole thing is moving, if I know the speed of the contact line is moving with a velocity of u sub c, where c is supposed to indicate it's a contact line, can I move into a frame of reference where the contact line remains stationary? Yes, absolutely yes. All we have to do is we have to define a variable, a coordinate, or we'll say we have to define a reference frame with a new variable. Let's call it as x hat, and this x hat is nothing but x minus uc times t. If we do this, all we will see is that the problem has essentially become as follows. We have a plate here, we have a contact line. Now the contact line itself becomes stationary in space. So this is stationary with respect to an observer in that frame of reference, but the plate as a whole is going backwards with a velocity of minus uc. I mean, I'm showing arrow and also saying it's minus uc. but the plate is going that way. Maybe I'll just remove the minus here. The plate is going backwards with a velocity of uc. When that happens, the motion of the the motion of the contact, the entire thin film is being compensated by a vertical upward motion of the plate in that frame of reference, and in that frame of reference the contact line essentially becomes fixed. This is often how it's very convenient. Many times we do experiments in such a frame of reference because we have precisely a control on the position, the location of the contact line. If I want to study, let's say, flow field near a contact line, or if I want to determine the shape near the contact line, then it's convenient to observe the phenomena in a frame of reference where the contact line remains fixed in position. Therefore in time as well, because it's not changing. Okay. So if I do this, then I simply have the interface h naught of x, h of x comma t essentially becomes some h naught of x hat. Note that there is no time anymore here, x naught of h hat. So we just have to modify the condition at y equal to 0, right? What was the condition at y equal to 0 that we had? The condition at y equal to 0, I'll highlight it in a minute here. This was the condition at y equal to 0. This has to be modified. It is not y equal to 0, but it's u equals minus uc, right? So condition 9 at y equal to 0 now becomes u equals minus uc at y equal to 0. We'll give this a label. We'll call this number 18. I think the numbering is fine. Okay. Now what we see is that the interface as a whole is flat in that region, and because we are actually moving backwards, the flow field that we see here would essentially look like this. In that region, right? So let's basically write down the conditions, more conditions now. The interface remains flat near x hat is equal to 0. So in this region, in the flat region, in the flat film region, the velocity will simply be, the equations would be uyy becomes minus 1. Where do we get this condition from? The equation comes from looking at equation number 3. Equation number 3 says the pressure gradient, which is basically the capillary pressure gradient, would be uyy, the viscous term, plus gravity. But if you say that the film is flat, then there is no capillary pressure gradient. Px is 0. So uyy essentially becomes a minus 1. We can integrate this 2 times with the condition with u equal to minus uc at y equal to 0, and we also have the condition uy equal to 0 at y equals plus 1, right? That's the condition we have. I just realized that made maybe a small error. Well, it's okay. Now there's no error here because the interface essentially becomes 1, because we have chosen the non-dimensionalization such that the thickness is d. So in this region, the dimensional thickness is d, right? And the non-dimensional thickness is 1. Therefore, I simply have, if I integrate this twice and use these boundary conditions, I simply get u as a function of y, it will become minus half y square minus 2y minus uc. This is 19. Okay. Now the total integral of this quantity, if you calculate it, the total integral quantity has to be 0. Why should it be 0? Because what is really doing is we want the entire film to be stationary. Let me write that down. Total integral of 19 has to be 0 to prevent the interface from changing shape. Because if there is a net flow rate into the interface, then what's really going to happen is the interface will locally bulge in a few places and deplete in a few places, and that will lead to change in the shape of the interface. So actually, technically speaking, this drawing is actually not completely accurate. Maybe a better drawing would be as follows. We would have something like this. So we have a portion of the film being dragged upwards, a portion of it is actually coming down, so that the net flow as a whole is 0. So if we do this, therefore using 0 to 0 to 1 u of y dy equal to 0, we get uc will be exactly equal to 1 by 3. I would like you to try and do this yourself. It's a very straightforward integration. You get the velocity of the plate is exactly equal to 1 by 3, so that the gravitational, to compensate for the drainage flow downwards, you need to make a plate move upwards with a velocity exactly equal to 1 by 3. Of course, in this non-dimensional setting. Therefore, I have x hat simply becomes x minus 1 by 3 of t, and we can also we want to get the time derivative here. Del h by del t in the original equation using the chain rule simply becomes del h naught by del x hat, del x hat by del t. Note that I have said that h of x comma t is same as h naught, right? And therefore, when I take a derivative of this quantity del h by del t, I can simply write it as del h naught by del x hat, and this simply becomes minus 1 by 3 del h naught by del h hat. Okay, I'll simply call it as minus 1 by 3 h0 prime, where this prime essentially denotes del by del x hat. The x hat is the derivative in that moving frame of reference. Okay, so if we substitute this, substituting into our original equation was equation number 14. That's my original equation is 14 here. If I substitute it, the other derivatives don't change because derivative with respect to time only comes in. The derivative with respect to x simply becomes, or maybe write this down. Just for sake of completeness, del h by del x simply becomes del h naught by del x hat by del x, and this del x hat by del x is simply 1, and therefore I have del h naught by del x hat, which is h naught prime. So that doesn't really change. Substituting into 14, we simply get minus h naught prime by 3 plus 1 by 3 times h naught cube h naught triple prime whole prime plus h naught square h naught prime is 0. We can do some rearrangement here. The rearrangement is as follows. We can get h naught cube h naught triple prime whole prime plus h naught cube whole prime minus h naught prime is 0, and therefore I get I can integrate it once. Integrating once, we get h naught cube h naught triple prime plus h naught cube minus h0 is a constant c, right? Now we can use the condition that at x hat is 0, that is in the thin film, we have h naught is 1. So the problem that we are looking at now is as follows. We have a thin film here. The location of the thin film here is x hat of c. Somewhere here in the uniform thin film is where we have x hat is 1, x hat is 0, and my origin begins from there, and this is y hat. This location, exact location, is y hat is equal to 1. That location is exactly y hat is equal to 1. Y hat is equal to 1. That's also the value of h naught at that location. Okay, but anywhere else we have the height is given by y is h of x hat comma t. By the way, there is no need to write a y hat there. Y is sufficient because we have only rescaled in the x direction, not in the y direction. So y becomes h of x hat comma t. Sorry, this is another mistake I made. It is not x hat comma t, it's just x hat. H of x hat. It's only a function of space, not of time, right? So this is what we have. Now if we basically use this condition that h naught is 1, we simply get c equal to 0. Therefore the equation that we get after simplification becomes h0 square h naught triple prime is equal to 1 minus h naught square, right? So, or we get h naught triple prime is equal to 1 minus h naught square by h naught square. This will give it a label. We'll call this as 21, right? Well, I guess I didn't really define label 20 at all. We can call this as label number 20. This, or maybe the one below, was 20. So we have all the equations now. The boundary conditions for this problem now becomes, it's a cube third order equation, third order nonlinear equation. H naught prime at 0, that is in the thin film region, is 0. We have h naught at the contact line is 0, and we also have h naught prime at the contact line, that's the slope, simply becomes minus beta. This is my equation, and this is a boundary value problem. Equation 21 with 22 is a boundary value problem, BVP. Okay, now we'll look at the singularity at the contact line that emerges when we try and look at the solution. Now, how do we solve the, typically it's a highly nonlinear equation. Typically needs to be solved numerically, but we will encounter convergence issues. Why do we encounter convergence issues? Well, for that we need to understand what is the nature of the solution as we approach the contact line. Okay, so for that we'll have to look at the shear stress singularity. The shear stress singularity is as follows. Now let's do one thing. Let's look at the equation 21 and ask, I can't fully solve this problem everywhere analytically, but is there a way for me to get an approximate solution very, very close to the contact line? So in other words, let us analyze the solution of 21 near the contact line. So that is as x hat goes to x hat c. That's what we want to do. Okay. So now notice that if you look at this equation 21, h naught goes to 0. The denominator of 21 in the right hand side goes to 0 as you approach the contact line. That's the second boundary condition in 22. So therefore this becomes a big headache for us, because when this goes to 0, the denominator in this term essentially vanishes. Equation 21 vanishes. That means that h triple prime has to go to infinity. So let me just write that down. Since h naught goes to 0 as x hat goes to x hat c, equation 21 requires h naught triple prime goes to infinity near x hat is equal to x hat c, near the contact line, correct? So this straight away you can see that this is the source of the convergence issues that I was talking about. Okay, now this is problematic. So we will also see this in terms of the singularity. We haven't seen the singularity yet. This isn't the actual singularity. We've seen that the equation has a problem, but we will also see the singularity when we analyze the shear stress. Okay, let us evaluate the shear stress at the solid liquid interface. That is at y equal to 0. So what is the expression for shear stress? Shear stress is actually viscosity times del u by del y, but we will put the viscosity term aside. We'll just calculate the velocity gradient. The velocity gradient at y equal to 0 simply becomes, this is just coming from the velocity profile that we have already obtained. The velocity profile is given by 19, right? So if we do this, we simply get minus half hxxx plus 1 times 2y minus 2h. This is at y equal to 0. And this simply becomes h times hxxx plus 1. This is the velocity gradient, right? So this is in the original frame. In the moving frame, the velocity gradient again becomes exactly the same. Simply becomes h naught times h naught triple prime plus 1. And you can clearly see that the problem now. H naught triple prime is there, which is becoming very large, right? So this is nothing but h naught. I can substitute the expression for h naught triple prime. What was it? It was 1 minus h naught square by h naught square plus 1. And that is simply goes like h naught times 1 by h naught square, which is 1 by h naught. So in other words, what we find is that the velocity gradient, which is related to the shear, which gives us the shear stress, this goes like 1 by h naught. This is a very troubling matter because the shear stress is diverging, and if the shear stress is diverging, it means that as we approach the contact line, the shear stress becomes singular, right? So if I were to make, if I look at this solid plate, and if I say that the contact line is somewhere here, and make a plot of the magnitude of the shear stress in this case, or rather maybe let me make it as a horizontal plot. This is along the solid wall, and we have xc hat, xc here, x hat is 0 here, and x hat's contact line there. So what I want to do is we want to see what happens when we go there. So the shear stress by and large remains constant and finite, but then when you approach the contact line, it diverges. And diverges, how does it diverge? It diverges as 1 by h naught, where h naught is the height and h naught goes to 0, right? So this is a bit of a problem now, and how do we fix it? Well, there is no simple way to fix it. In fact, the problem is even more worrisome than just the algebraic kind of divergence that we see for the shear stress, because one can always say, well, the shear stress may diverge. That's not a big headache for me. What is more important is, what about an integrated quantity, let's say like dissipation or the net force? What about such a quantity? One could say, as long as the overall dissipation is not diverging, then I'm okay. Or as long as the overall force is not diverging, that's okay, because shear stress is its force per unit area. But if one could say, if I integrate it over a smaller and smaller area, because this divergence is so confined to such a small area near the contact line, maybe if I integrate it over a finite area, or in other words, instead of shear stress, if I look at force, maybe the force will not diverge. If that happens, then I'm okay. That could be an argument, right? So let's calculate the force as well. The force is in this case we're calculating the tangential force. The tangential force, we'll call it as F, and this quantity goes from x hat to x hat c. So what I'm really doing is I'm integrating it from some location x hat all the way towards the contact line, and I'm asking, if I shrink this quantity, if I go closer and closer to the contact line, what happens to this force? So uy at y equal to 0 along the surface, so I'll just say along dx, okay, and I should actually add, say, for viscosity, okay, and this quantity simply becomes mu times, this is an improper integral here, okay, x hat c minus, I'm approaching it from the left side, going from x hat to capital X hat. The dominant term is just 1 by h naught. This is my equation number 26. Okay, here we have used the definition of an improper integral. Now, if x hat is sufficiently close to the contact line, we can approximate the local interface shape. We don't know, we can't do this integration till we know the how h naught is varying with x. We'll call it as ds. Okay, so till I basically go towards the contact line, we need to know what is the h naught of x. If we are sufficiently close to the contact line, then we can say h naught of s can be approximated as some parameter. Let's call that parameter as minus delta of some S minus x hat of C. Okay, so in other words, we are just saying that locally it's a straight line, it's a wedge. This is h naught of x hat, and this is S here, and this is nothing but x hat of C. Okay, and this quantity is basically my delta. That's what we are essentially saying. This will call it as 27, and therefore if we substitute this, we simply get f goes from minus of x hat goes to x hat of C minus, this goes from x hat to capital X hat 1 by delta S minus xc. That's what I'm just substituting for S, and this gives me integral of, we all know, integral of 1 by S minus x hat ds by this is simply nothing but a logarithmic term. So the logarithm term would be as follows. I have x hat going towards xc, this is minus, we have 1 by delta times logarithm of xc minus capital X hat. We also have minus logarithm of xc minus x hat. And this quantity here, as you approach, as x goes to x hat, this quantity becomes infinity. So what we find is that the force that as one approaches the contact line, even the force basically diverges. Okay, so I think with this I'll stop here. As far as the singularity is concerned, one can also show that the pressure also diverges exactly in a similar fashion. So this singularity cannot be removed. So we have a logarithmic singularity, which is a very strong singularity. And the primary reason for this is that if we say that if we apply the no slip condition, that is exactly what we have done so far. If we apply the no slip condition, we get this singularity. Now it's important to remember what I said at the very beginning, that the singularity is not just a feature of the lubrication approximation, but it's a feature of moving contact line problems itself. In fact, we will be briefly discussing the singularity that was in some sense discovered first by two gentlemen, Herr and Scriven, in 1971. It's sometimes referred to as the Herr-Scriven paradox in the moving contact line literature. They actually used a rather interesting Hellenic verse to explain this singularity, and they say not even Heracles. Heracles is the Greek, the Hellenic name for Hercules, and as you know, some of you may remember, Hercules is considered to be one of the most important among the pantheon of gods in Greek mythology. He's considered one of the most powerful gods. And Herr Scriven quipped that not even Heracles could sink a solid if the physical model was entirely valid, which it is not. They actually said that if this force was infinite at a solid wall, which it means that I need an infinite amount of force to move an interface on a solid, or move a solid with an interface. So if I think of a small experiment, if a small solid is basically resting on a fluid, if I have to move the solid up and down, then I would need an infinite amount of force. This also is true for, let's say, a droplet moving down an inclined plane. If you have a droplet moving down an inclined plane, there is a singularity at the contact line. If you apply the conventional boundary conditions, then it means that I need an infinite amount of force to make the droplet move. But we know that is not the case. If you just blow a puff of air on the droplet, we know that the droplet will move. So the force is clearly not infinite. Therefore, there is a paradox in some sense, right? So how do we resolve this paradox? Well, there have been several suggestions to resolve this paradox. One suggestion is that there isn't really a contact line per se, but rather there is a thin film ahead of the contact line. It's called a precursor film. Okay. A precursor film essentially says that there is a very, very thin film of a very small thickness, which completely removes the contact line problem per se. And it allows us to proceed further. And there is some experimental evidence for certain class of problems where there is a precursor film. The only thing is that this precursor film is often only a few angstroms and several nanometers thick. There is another suggestion that the no-slip boundary condition is the culprit. Therefore, perhaps the no-slip boundary condition itself is not valid. There is also evidence to say that the no-slip boundary condition is not. If you basically look at a more kinetic theory based approach, then you can actually come up with an expression for the effective slip length, meaning that's the length scale over which the interface basically the fluid actually slips over the solid. The no slip boundary condition is not strictly valid. There are other suggestions as well. A diffuse interface approach, which essentially says that the interface is actually not a mathematically thin surface as we have been doing so far, but rather it has a finite thickness, and there are additional processes such as diffusion, length scale, and the width of the interface thickness which comes into play. There are more recently there has been a very interesting model called the interface formation model, which essentially says that you think of the interface every time a contact line moves, a fresh interface is forming. In this model, the surface tension as a parameter is not held constant, but rather it's allowed to relax over a certain time scale. So there are several of these suggestions, both from kinetic theory, from non-equilibrium thermodynamics, plane slip models, diffuse interface models, precursor film models. There have been several of these models. So one of the things that these models aim to do is to come up with a relationship between the speed of the contact line and the contact angle. Note that in our model, we have basically said that the contact angle, which we called the contact angle, was considered to be fixed, which we called as theta at the beginning. This contact angle does not depend on the speed of the contact line. But that is not the case. Experiments do observe that the contact line does move. It has a finite speed and the angle does change. So what we will do in the next lecture is to briefly look at some of the standard approaches to elevate the singularity. And we'll look at one such model, a very, very simple model, which gives us a relationship between the dynamic contact angle and the contact line speed. Okay. Note that I'm talking about dynamic contact angle, not just contact angle. It's a dynamic contact angle because it's a moving contact angle versus speed. So we'll look at one simple model, a mechanical model, where some kind of a cutoff has been put to remove the singularity, a cutoff near the contact line. But of course, these are problems of active research, and this will take us too far away from the course. And further, I am also not fully qualified to talk about these problems in great detail. So we'll stop it here, and we'll look at a simple contact line model in the next lecture. Thank you.